So the bipolar, meaning two poles or two junctions, transistor. We refer to these as BJTs or transistors. We need to get used to in this class for not using that term because like I said, we got 8 different transistors that would fall under the category of transistors. We have BJTs and we have FETs. And we start off with the BJTs and we move into that. But if we understand how a water valve works, and you know y'all don't understand how these things work. So what a transistor is, it's a current valve. So we got a knob here that we turn, that we get a mechanical advantage of. So you can go up there all day long and turn that faucet on, and you can put your hand under there and try to stop that flow. You can't stop that flow. But you can take that little old tiny valve and you can stop the water. I can go out there and take that little valve and turn on water to my ice maker in my refrigerator. I can turn on water with my washing machine with this valve because we get a mechanical advantage. So what a transistor is, all transistors are current valves. The only changes is how we change the size of the valve. So the actual valve, so this is the symbol we've already looked at a little bit. We call this the what? We have the one with the arrow on it, we call that the emitter. The one without the arrow, we call that the collector. And that's our valve right there, guys. That's the valve. It's the one, it's the current flow between the emitter and the collector. And instead of controlling the flow with a knob, we control that flow with this guy right here. So the more base current I put into it, the valve opens. The less base current I put in it, the valve closes. So I can control the flow between the base to emitter, between the emitter and the collector by putting a very small, what we call base current into it. So we use very little force to control our water valves, but we're controlling a lot of force even though we're using a small valve, right? Because we get a gain, but in a water valve we're getting a mechanical gain. If you ever looked at a water valve, it's got a screw thread in it, and screws are very fine, and that's what so it takes a lot of turns to turn on your water fountain, right? Because of the gain. So this is what a transistor does. A transistor is a what? It's a current valve. Bipolar transistors, we can control it between two leads called the emitter or collector. FETs, the two leads are called the source and the drain. But if you understand this, we're going to be able to pick up on transistors really easy. Transistors are electrically controlled current valves. We have two categories. We have bipolar junction transistors, or BJTs. This uses a real small base current to control a proportionally larger emitter to collector current. Normally we don't call it the emitter to collector current, we call it the collector current. And we'll see why, because a field effect transistor uses a small gate, and I left off something. So let me get this. Uses a small gate voltage to control a proportionally large drain to source current. So FETs we control the valve with a voltage. BJTs, we control the valve with a current. And that's the difference right there. That's the big difference. We have 3 regions, right? We have what we call the emitter, base, and collector. And we have 2 junctions, hence the name bipolar. So we have a junction between the base and the emitter, and we have a junction between the base and the collector, right? Everybody okay? And so this would be an NPN and a PNP. So what we do is we have a small region called the base sandwiched between 2 other regions, which are fairly larger. So an NPN transistor would have a P material sandwiched between 2 N's, and a PNP would have an N material sandwiched between 2 P's. And this is our junction right here. So we call this junction right here, we call this the base to emitter junction. Base to emitter junction, we call this the collector base junction. And of course, to make this thing work, we have to forward bias the base to emitter, and we reverse bias the base to collector. We'll see why that causes things to happen. So I just got to explain that. It's most commonly used because why? Because it works predominantly off a positive power supply. And we'll run into a lot more positive power supplies than we do negative power supplies, even though they're out there. Are we okay? The emitter is heavily doped. The base is lightly doped, and the collector is moderately doped. And this is what causes this thing to work. So what that means is the base has very few places where the emitter current can fall into. The P-N junction joining the base region and the emitter region is called the base emitter junction. The P-N region that forms the collector is called the base collector junction. We've already talked about that. So we're going to call these, Yes. So what we do is we got a lot of majority carriers in the emitter. We got a very few majority carriers in the base. So what's going to happen when that emitter starts dumping all those majority carriers into the base? They're not going to have anybody to combine with, right? So that means if it's an NPN, that means the emitter's got tons of electrons in there, and the base almost has no holes. So all these emitters, when we forward bias that junction, all these electrons start falling into the base, but they don't have anything to fall into. And then up there on the collector, we're going to have a really big potential on the collector. The collector is going to be the highest voltage potential up there. And that collector is going to suck those carriers right through the base. And that's the way it works. Are we okay, Courtney? So these are two symbols. And Courtney said the emitter points down or down or up, but we can draw the symbol with the emitter pointing with an NPN pointing up, right? Does that make sense? So what we look at is we look at that arrowhead right there. And then we just say it's not pointing in, which would be a what? An NPN, or it's going to be pointing in, which would be a PNP. So here is not pointing in, so I'd start off not pointing in. And over here pointing in, I'd start off P, N, and then of course we don't have anything for the P. So pointing in and not pointing in, that's the way we identify this. So the one with the emitter pointing out is not pointing in, is the NPN, and the one with the arrow pointing in is the PNP. Are we okay? In order for the transistor to operate properly, two P-N junctions must be supplied with external DC voltages to set the operating conditions, and we call that bias. The base to emitter junction is forward bias. The base to collector junction is reverse bias. Since the base to emitter junction is forward bias, we refer to it as forward bias. So it's just a term that we use, even though that's just a generic term in this situation. Are we okay? Are we okay so far? The forward bias junction the forward bias forms base to narrows the depletion region. The reverse bias collector junction widens the depletion region. The heavily doped emitter region is packed with free electrons that easily distribute through the forward bias base to emitter junction. So this is what we have. So I come over here. So this would be an NPN. So notice what we do. So here we put the positive here is pointing toward the base. The negative on this supply is pointing toward the emitter. So that P-N junction is forward bias. Okay. So here comes, that's going to start, now it's forward bias. Of course, we've got to have this resistor to limit the current right now, right? While we're learning this. And right now we're going to do two power supplies. We're going to use what we call a two power supply bias. This is the way we start teaching bipolar transistors. This is the way we start. Okay. But later on, we're going to move into a single power supply bias, and we'll see how that works. Thanks, y'all. So what happens is as soon as I do this, we start having current flow. So the current flow is in this direction right here, right? Everybody understand that? Now what we got, as soon as that forward bias is all these, since this is an NPN, all these electrons spill into the base, and we don't have very many holes for them to combine within there. These electrons have a negative charge, and what does it see up here? It sees that big old positive charge sitting right there. Electrons are attracted to the positive, so 99.9% of the current flies up through there and goes around this loop right here. So about 1% of our current. Now look, what do you have in the emitter? You got two currents in the emitter. So the emitter current consists of base current and collector current. So what's the emitter conducts the most current in the transistor, followed by the collector, followed by the base. So the highest current in the transistor is in the emitter. But we're talking about, so 99% of the emitter current goes into the collector. It's only about 1% that goes into the base. So for all practical purposes, just to keep our sanity, we're going to assume that the emitter current and the collector current are basically equal to each other. They're not, right? You understand that. But there's such a small difference between the emitter current and the base current that it would be extremely hard for us to even know the difference. Now notice on the PNP, we're biasing these with negative voltages. So notice here we have the negative pointing toward the base, and we have the positive pointing toward the emitter. Now over here on the collector supply, I have the negative pointing toward the collector, and this is a PNP. So we're reverse biasing that, so the base is going to be positive in respect to the emitter. So to make these things work, we have to forward bias the base to emitter junction, and we have to reverse bias the base to collector junction. And once we do that, then we're going to have conduction. Now, the size of once we have conduction, then the size of the valve is controlled by the amount of base current. So the more base current you put into it, the valve opens up and allows more current to flow. The less base current you put into it, the valve closes down and the less current flows there. So, but we can precisely control that current with base. But first of all, you got to make it conduct, right? You understand? So what do we got to do to make it conduct? If this is a silicon transistor, that means I've got to have at least about 7/10 of a volt sitting on the base. If I'm below 7/10 of a volt, then the valve is totally closed. We call that situation cut off. The valve is cut off. So if I don't put 7/10 of a volt there, if I don't put 7/10 of a volt there, I don't have base current. If I don't have base current, I don't have collector current. Now I can keep increasing the base current until this resistor right here drops all the voltage. When this resistor right here drops all the voltage, I can put more base current. Once a water valve is open, right? You understand that. So normally when you're turning your water valve, you get maximum flow before you top out. Because the valve has got a orifice big enough to let the flow rate of the water system to come through. Once it gets to that point, I can open that valve up more, and you can't get more water than's available to flow, right? You understand? So if your system is giving you, 3 gallons per minute, once you get 3 gallons per minute out of that valve, you can keep opening it up. You're not going to get more than what current's available. So what we're looking at is we're looking at this collector resistor right here. So if I put 10 volts right there, and once that collector resistor drops 10 volts, how much is being dropped by the resistor, by the transistor? How much? I got 10 volts applied. The resistor's dropping 10 volts. How much is dropped by the transistor? 0. Yeah, so the switch is, so now the switch would be what we call closed. So we call this, for the obvious reasons, we call this saturation. Because the transistor, so you can, once that collector resistor drops all the voltage, you can put all the base current in the world you want to. You can't open up a valve more than the maximum flow it can handle, right? Does that make sense? And we call that saturation. So we can switch a transistor between cutoff and saturation, and it acts like a switch. To cut it off, I just drop this voltage below what? What, about 7/10 of a volt. As soon as I drop it below 7/10 of a volt, there's no base current. Transistor cuts off. Then I start putting base current on it. Sooner or later, this guy right here is going to drop all the voltage. When it drops all the voltage, can't drop any more, or the Kirchhoff's law, right? You understand? So the transistor acts like a closed switch, sort of. We get confused with the current in the same direction. So here, normally on transistors, we don't trace current flow, because what would happen is that in this one, I would draw the arrows in the opposite direction. So in this one, my base current would be going this way. And then my I got the colors backwards, guys, but that's okay. And my collector current would be flowing this way, because current flows from negative to positive. But we still have current flow, and they operate basically the same way, right? You understand? All it changes basically is the direction of current. And we still have to forward bias. But notice, what are both these? If this is common right here, then notice we refer to these as negative power supplies because the positive is common. But here the negatives are common, so we refer to those as positive power supplies. So this is why the NPN is used more often, is because the predominant power supply out there is positive power supply. But just because you have a positive power supply doesn't mean you can't get negative and positive voltages out of it, right? You understand that? By electronically causing things to happen. The base region is lightly doped and very narrow, so that it has very limited number of poles. This is for NPN. Now, if it was a PNP, what we're saying, everything would swap around. Only a small percentage of the electron flowing through the base emitter junction can combine with holes in the base. This generates a very small base current. Most of the electrons flow from the emitter into the collector depletion region because they are pulled through by the reverse bias base to collector junction by a very large positive collector voltage. So the collector voltage is going to be real high. It's going to be a real high positive relative to base voltage. It's going to be real high relative to the base voltage. It's going to be a higher positive for a NPN transistor. It's going to be a higher negative for an NPN, for a PNP transistor. The electrons are pulled through the reverse bias base to collector junction to the collector power supply. And that's the way these guys work. Electrons move the collector region out through the collector lead and to the external collector voltage supply. The amount of collector current is controlled by the watt, the amount of base current. So as soon as we hit about 7/10 of a volt, we start getting base current. The transistor, the valve starts opening. But it's going to have a lot of resistance. As I keep increasing that base current, the valve opens and lets more current through until I get up to the maximum flow, which we call saturation. And basically, the collector resistor, or the loads you put in the collector, would, and we can put all kind of loads in the collector, guys. Well, here we're putting a resistor, right? We can put all kind of loads up in that collector. We can put relay coils up there, so we can turn relays off and on with this guy. We can put LEDs up there. We can put light bulbs up there. We can put anything that operates off DC up in that collector. And we can control it. But what we're doing is we're getting a lot more collector current than we are that's required to control this thing. So this is this is not in your book. This came out of a Prentice Hall book. But this is a really, really good example of what's going on. So we got that big old collector side. It's going to be opposite of what the emitter is, right? You understand that? So if the emitter's an N, that means it has a lot of electrons. Then we're going to put a big old high positive up on that collector. And when these guys come flowing into that base, they don't have any holes. They don't have any holes to fall into, and they see that big old positive potential up in that base, sucking those things up, right? You understand? So about 99% of the current goes up through the collector. And we got a ratio we'll talk about. We'll call beta, which is in this chapter. It surprised me that nobody asked about beta, which is a really good question. So let me hook up my speakers. Hopefully they don't make any crazy sound like they normally do. And we'll play this video. This is off YouTube. But we might have to watch a commercial first. At least it was funny. What do you think? Pretty interesting, right? I think it's a pretty good explanation of how the thing's actually working. And he's got a visual effect. The guy's holding the. This would be a good one to actually show for diodes too. Just cut it off right there because the way he does it. Another guy dresses up. He does it himself. It's basically the same video. I wish I could show you that. When I started looking at it though, we might look at that one. He basically talks about an FET. So we'll look at that one when we get into the field effect transistor. So, are we okay? Are we okay so far? Any questions? Okay, guys, y'all take a 2-minute break. Textbook. We're going to add a little more to it. But everybody okay here? We're okay so far? Any questions? Small base current can control a large collector current. Of course, Kirchhoff's current law says the current flow into a junction has to equal to the current flow out, right? You understand that? So it says, therefore, the sum of the collector current and the base current equals to the emitter current. And I don't know what goes on here, guys, because this is going to be in several tests, and I'm going to ask which current is the highest in a bipolar transistor. Emitter current, base current, or collector current? Which is the highest? Emitter current is the highest. It's the highest current. And so this is the basic formulas which the book don't teach, but it's pretty straightforward. So IE is equal to IB plus IC. IE is the largest current in the BJT. IC is the second one. It's equal to IE minus IB. And so all we're doing is rearranging the first equation. So IB would be equal to IE minus IC. So oops, I made a mistake. I just put this in. I just put that in before class started, so it's not in the blackboard. So IB is the smallest current in the BJT. Since IB is so small, what we're going to assume when we start calculating these circuits, we're going to assume that IC and IE are equal to each other. But if you see a question that says IC equals IE, you're going to answer what? What's the answer to that? True or false? IC equals IE. Is that true or false? It's false. I just got to, how can it be equal when how can IC and IB be equal to each other if IE equals IB plus IC? That would be like saying if IB was 0, then that might be true, but it's not. So IE and IC can never be equal to each other. IE is the largest current in the transistor. Now, if it says IC is approximately equal to IB, that would be true. But the trick there is approximately and equal to, right? They are never equal to each other. Well, none of the currents in the transistor are equal to each other. The largest current is what? The emitter current, followed by the collector, followed by the base. They're almost identical, but they're not. So for calculations purposes in our math, we're going to assume we're going to use them as being equal, but they're never equal. But they're so close, it's not going to affect our math. And why is that? Because we got so many dang tolerances in the system, right? You understand that? Like in DC, we talked about this in DC. What did you do? You measured your resistance because you were trying to prove Ohm's law. But we understand Ohm's is a law of physics, right? You understand that? When we get to this class, we don't measure resistors because now we understand if I calculate 2.5 volts and I measure 2.8, we understand why we have a difference between our calculated and our measured, right? You understand that? So for us assuming or using IC is equal to IE in our math, that's fine. But if you see a question that says IC is equal to IC is equal to IE, that is false. If we see IE is always greater than IC, that's true. Or IC and IE are approximately equal. That would be a true statement, right? Y'all think y'all will see that on the test? So are they equal? No. Are they approximately equal? Yes. So what we do, and this is not covered very well in the book, so notice the little squiggly line. That don't mean equal to. That means what? What's the little squiggly line mean? Approximately equal. So it's going to be close enough for a lot of our math. But you need to understand that IE is the largest current. Are we okay? Now we're going to skip ahead a slide. It says for me to go to electronic working, but we're going to look at one more little thing that the book doesn't do a real good thing of doing. We can operate the transistor in 3 different regions. We can operate it in saturation. And in saturation, it acts like a closed switch. But it will always drop a voltage. It is not a closed switch. So what when we look in the data sheet, we'll see they talk about the saturated voltage. It's going to be less than a volt. Then cutoff, the transistor acts like an open switch. So to operate it like a switch, we switch it between saturation and cutoff. That's what we do. To operate the transistor like a switch, we switch it between saturation and cutoff. Y'all understand that? We do that all the time. Then we have what we call the active region. Here, the transistor acts like an electrically controlled rheostat. So this is where we actually control the size of the valve. And this is where we get amplifiers. So audio amplifiers. Your audio amplifiers operate in the active region. Before it hits your speakers. Now we do a lot of digital stuff now. So our CDs are digital. We have digital radio now that we can get. By the time it hits those speakers, by George, it is what? It's analog. The speakers don't do analog. Don't do digital. They do analog. So we have these things called D to A converters, analog to digital converters. So to get those big old power amps out there, before we hit those speakers, all that stuff is back to the active region where we can use it like a rheostat. So let's look at this electronic workbench. And y'all got this on all these computers, by the way, but I'm not going to explain to it. So what we got is we got a little transistor circuit here that we got a lot of bench meters in. So we got this bench meter right here measuring the panel meter, I guess, measuring the voltage on the base. We got this meter right here. This is an ammeter. This is measuring base current. We got this meter right here. This is measuring voltage across the collector resistor. This guy right here is measuring emitter current. This is a current meter. This one is measuring collector current. So we're basically measuring everything that's going on in this transistor. Okay, I'm going to turn it off and turn it back on. And we look at our collector current right now. So notice on my base I have 0 volts. So the transistor's cut off. And then we up here on this meter it's showing 12 microamps, which is basically nothing, right? And a transistor is never ever truly off because there's a path current can get through there. So we'll always have a leakage current through the transistor, just like a diode when it's reverse bias. There's a leakage current through there. But it's going to be so small it's not going to do any work, right? You understand that? What I'm going to do with this potentiometer right here is I'm going to start increasing the base voltage. So right now we got it set to 0. So right now I've got the base connected to ground. And I'm going to start hitting the letter R. And so you can see right off the bat the voltage on the base goes up a little bit. Collector current's not changing. Here go up to 51 millivolts. Collector current's not changing because the transistor's still cut off. What's it looking for? It's looking for about what? Around 7/10 of a volt. As soon as it gets up that 7/10 of a volt, then we're going to start getting collector current. So here we come up. This is 100 millivolts, still 12 mil on here, so it's not doing anything. It's not doing anything. It's not doing anything. Okay, 180. I'm going to start jumping up pretty fast, guys. So here we're going to get up about 300 millivolts. 400, 500, here we go. Now it's starting, just now starting, but we're still in that knee, right? Here we come, then we're going to get up to 500 millivolts. We're getting a little bit of collector current, but we're still almost cut off. 600 millivolts, still not there. We're up to about 15 microamps. This guy's going to cut on probably right around in here. I think this guy uses 700 millivolts. But look, I'm putting, now I've got base current. I got 190 microamps of base current, and I'm getting 133 microamps of collector current. So we're getting a gain of what? 130. Okay, I'm going to come over here and increase a little more. Oh, God, I can zoom in on this. I'm sorry. I can see it real well. Now that's about the best I can do and still keep everything on the screen, guys. So here we're getting a 10 microamps, getting so 12 microamps in, 1 milliamp out. So what would be the current gain? How would we calculate this? Well, what I'm doing is, now look, the emitter current is the sum of the two. Of course, we can't really see it now because we're still in microamps. But what I would do to figure out the current gain, what's gain? Well, gain is always you take the out and you divide it by the in. So my out here in this situation is my collector current. So I would take 1.54 milliamps and I would divide it by 12.2 microamps. So what would be our gain in this time? A little over 100, right? Should be, huh? You got 12.2 micro, so it's going to be 1.15 or 1.2 milliamps divided by 12.2 microns. What we get? So, okay. And that's going to stay about the same. So here I'm getting in 31 milliamps. Now notice the voltage drop across the transistor is going down. Voltage drop across this guy's going up because what we're doing is we're opening up the current valve. And when this guy, so it means the opposition here is going down, which means this is staying constant. Well, if this goes down, total resistance in this series circuit goes down, current goes up, and the voltage drop across the fixed resistor goes up, right? Let's see that. So I increase it a little more, voltage drop across the transistor goes down, voltage drop across this resistor goes up because collector current's going up. So what we're doing, we're operating it like a rheostat now, right? You understand. But what am I controlling the resistance between here and here? I'm controlling it with this base current. So as I raise the base current up, the resistance between the collector and the emitter is going down. So we've got 9 volts across the transistor. We'll go up and we're going to put it in saturation in a minute. How do I know it's in saturation? When this guy right here drops the applied voltage, then I can keep putting base current in the thing and it's not going to do anything. But when every time we calculate the gain, it's going to stay around 100. So here we can actually see this. So 104, so see the gain is about 100 for this transistor. So that means for every current I put in, the collector current is going to be 100 times that. That's a pretty good gain, man. I wish I could get that on some of my investments. 1.5, this voltage gain is going down, this voltage is going up. But we're pretty close to saturation right here. So the top resistor is dropping 11.83 now, 11.84. So we're saturated right now. Pretty close to it. Okay, so we're saturated now. Now this guy will never actually drop all the voltage because it is a transistor. It is not a closed switch. So the transistor is still dropping about 125 millivolts. This guy here is dropping all the rest. But if we add these two together, it should come up and still give us 12 volts, according to Kirchhoff voltage law. So the transistor, we assume the transistor to be saturated when it drops less than a volt across the transistor. We assume it to be cut off when it drops the entire voltage. So it's cut off when it drops the entire voltage, when the transistor drops the entire voltage. It's saturated when this resistor or this load drops 90% of the voltage. And anywhere in the center, we call it the active region. So my amplifier is operated in the active region, where I'm using my input signal to control that base current, and I get a lot more collector current than I have base current, which is pretty neat. So to operate it as an amplifier, we use a stereo amplifier, those type of amplifiers. We're going to operate these things in the active region. Oops. Sorry, guys. Let's go back down. So now we're saturated. But look, the emitter current is what? Here's the collector current. Here's the base current. So the base current is 830 microamps. And this is actually kind of the math's off a little bit. 83.82 milliamps. Because this is the sum of this current and this current, right? Y'all understand that? So the emitter, so this guy's taking two currents. So this is one path for our current flow through this voltage over here. This is our other path for the current flow. This is the guy where all the power is coming from. The little old base battery don't have to provide much power, but that second battery over there has to provide all the power. So you got to understand, I'm changing the power in this resistor right here because I'm changing the resistance, but the amplifier is not changing the power. The amplifier is changing the current. Where does the power come from? From that DC source right there. So amplifiers don't create power. All they do is manage the power. They manage the power. The power comes from your power supply. So a lot of people think that transistors create power. They don't create power. They just manage the power that's already there. So that's what the power supply is for. That's why they're calling power supplies. They're not calling, right? We call them power supplies because their main function is to provide two things. It's to provide voltage and current, a push and then the current. Then we create a voltage drop by pushing current through that thing, and that voltage drop is where the power comes from. The power is equal to V times I, right? But where did the voltage source at? The voltage, this provided the voltage. If I didn't have this, I wouldn't have a voltage drop. If I didn't have this, I wouldn't have current. So that's why we call them power supplies. But ain't that neat? I mean, good gracious, you can almost see this now. That's 100. So for this transistor right here, this guy here has a gain of 100, which means that for every milliamp I put into the base, I would get 100 milliamps out. Now this is still what we call a small signal diode. I couldn't put 1 amp into it and get 100 amps out because this little transistor just wouldn't handle it. But we do have transistors that can handle that. Usually those have a lower gain. So your big power amp, your big power transistors will have a lower current gain. These small signal transistors have a really good current gain on them. So okay, ain't that neat? And this is a simulation. We'll hook these things up and see. The transistor that we're going to use has a gain of about 100. It's 2N39, 3904. It's the first, that's the NPN we're going to use. And it's got a typical beta of around, current gain of 100. By the way, I just spilled beans. We call that the beta. The beta of the transistor is the current gain. And that's the collector current divided by the base current. And books call it the beta. And the books, it's kind of like books call the maximum voltage a diode can drop. They call that the PIV, the peak and burst rating. But you look in the data sheet of a diode, you won't ever see PIV. They call it the reverse VRRM. So in data sheets, they call this H of FE, which is the hybrid forward transfer ratio with the emitter common. So you see the emitter is actually connected to common. So technically we call this H of FE. So that's the same as what we call beta. But we saw all three regions. We saw the active region when it acted like a rheostat, right? We saw cutoff when we dropped it below the voltage that was required to cut it on. We had no base current. If we have no base current, then the transistor cuts off. Acts like an open switch, but we still saw a little bit of collector current, but it was way down in the microamps. Because guys, you have to understand, it is not an open switch. It is not a closed switch. It's a transistor. It's a semiconductor that's been doped. A semiconductor will always have a little bit of resistance, and they'll always have a leakage current because there is a path. If I open a switch, there is no path. But a transistor, we always have a path for current to get through that. And we call those leakage currents. But they're very small. So what I can do now is I can put a little old tiny push button on the wall. I can go over and touch it, and I could turn on all kind of lights because now I'm using a very small current to control a very large current, right? Proportionally large current. Oops, I don't want to know that. Wrong computer. And what's really cute about electronic workbench is we can draw a schematic and it simulates the schematic for us. So these are our three regions. Y'all understand that? Saturation, it acts like a what? Closed switch. It's not a closed switch. It will always drop a voltage. And what's the cutoff? We usually assume if it's below, if the voltage across the collector and the emitter is less than a volt, we assume that it's saturated. Cutoff, the transistor acts like a open switch. Now this guy is going to, with the meters that we have available, the applied voltage will be across there. Because you saw that was down in 83 microamps, you know. How much would a 10K resistor drop with 83 microamps on it? Almost nothing, right? Y'all understand that? So odds are if you got it cut off, you're going to measure the applied voltage across the transistor. In the active region, it's going to be somewhere between 1 volt and the collector voltage. So that's a voltage that we're going to talk about. We'll understand how we designate these voltages. And I tried to put them all inside that glossary that we put out for you. So beta, it covers this, but I looked for it in this chapter. I thought I saw it once. When a transistor is operating in the active region, the collector current is proportional to the base current. The DC beta is the current gain of the transistor and is the ratio of the collector current to the base current. And you're going to see a lot of our loads we collect up there in that collector. And what we're going to assume, it's not true, but we're going to assume that the emitter current and the base current are equal to each other. I'm sorry. The emitter current and the collector current are equal. We're going to assume it just for math purposes. but we know that they're not, right? We just saw that, happen. But look at the difference, guys. I mean, good gracious. So on this one, my base current is 830 microamps. My emitter current is 83 milliamps. 83.82 milliamps. My collector current is 83 milliamps. So that's only 800 milliamps difference. That's only about 1 milliamp difference between me saying what they're not equal and then assuming they are. So if I did math and I used, if I did math and I did 80, if I did math and I did 80, if I did 83, if I did 84 milliamps and 83 milliamps, the math is not going to be that much difference anyway. I knew it was in here somewhere. Transistor current gain. Now gains, no matter what we do, a gain is always what you get out divided by what you put in. So we'll calculate power gain later on. So power gain is going to be what we get out of the amplifier divided by what we put in. And of course, in amplifiers, the ultimate goal is to get a power gain. Of course, power is work, right? You understand? As a transistor switch, what we're trying to do is we're trying to get a current gain out of it, which means my control current is going to be real small compared to what I'm trying to control. So it means now I can turn these things on. I can turn this light bulb up on right here. Instead of me flipping a little switch, I can push a remote over here, and it's got a device that takes very little current to turn the light on, and I can also do what? Turn it off. It wouldn't surprise me if it was I don't know if it's a transistor or not, but it's going to be some solid state device that I can do what? That I can use a very small current to either turn it what? On or turn it off. This guy here is made up of thousands of little old tiny dots. Did we look at them in this class? And that's all we're doing. We're either turning those things what? On or we're turning them off. When we process information inside a computer, that's all it deals with is on and off. So he said that processor in there had over 2 billion transistors using like what they call a 20 micron technology. By the way, the problem they've had is with the size of the conductors connecting everything together. So that kept us off for a little while. Originally, silicon didn't get along with copper. So what we had to do for years is we had everything that touched silicon, we had to use aluminum. So everything that goes up there was aluminum. IBM finally figured out how to put a real thin coating on the silicon, and they came out now the processors use copper for conductor, and that really jumped the speed on the processor. They call that the copper mine processor. Beta is a constant ratio called the current gain and is usually designated as H of FE in data sheets. When we get into the data sheets, we're going to look for H of FE. And it basically stands for the hybrid transfer ratio with the emitter common. That's what it means. And if you go back to that circuit, the emitter was connected to the common of the circuit. Are we okay? So far, so good? So these are the formulas right here. So if I know then we can transpose this, and I can solve for IC. If I measure IB, I can solve for IB if I know what IC is. And beta is a given, or I can solve for beta. The beta is given in your data sheet, but we have a real problem with beta. The problem with beta is that, well, number one, it varies with temperature. So if temperature goes up, beta goes up. If temperature goes down, beta goes down. So this is why we have to be very concerned with semiconductors getting hot, especially transistors. We'll look at later on how we compensate for that. This should be on your formula sheet. Okay? And the first thing we're going to do is learn how to design a switch, transistor switch. We have another rating that they don't cover this in the book very well, but it's called the DC alpha. The alpha would be, and this is going to be what we'll use. So what we have different ways we can connect the transistor. We got 3 leads. And what we do is we go about and we make different leads common to the signal. So this one right here, this arrangement right here, we call this a common emitter. And this is real easy to do. So notice my signal is common. Here's my signal coming from this battery. It's common. And then this right here is common. So we call this arrangement the common emitter amplifier. And this is probably one of the most popular arrangements out there. And we'll talk about why. And then we got 2 other ways we can hook these things up. We got what we can call a common collector, and we got what we call a common base. A common base is probably the one used least often. Common collector is the guy. It's a current amplifier. Your common collector gives you tons of current. It don't give you voltage, but it gives you a ton of current. And of course, when we hit speakers, we want a lot of current, right? Because they work off of magnetics. So usually on amplifiers, you end up with a common collector to drive the speakers. And we'll look at why. We'll talk about what we call impedance matching and all this other kind of stuff. We'll learn a lot of stuff of why things are the way they are in this class. So this is called a common collector, and this is probably the most, this is the common emitter. This is the most widely used amplifier out there. Saturated switches, or switches, this is the guy. Common emitter is what's used for saturated. I keep trying to switch applications, and I'm on the wrong computer. So alpha is, if we're using a common collector amplifier, now, they usually don't give alpha. So alpha, the alpha of the transistor, so this is the Creek symbol for alpha, and these are DC, is equal to IC over IE. Well, what can I say about this thing? Is this thing will always be greater than 1? So beta is going to always be greater than 1. What about this guy? Is it going to be greater than 1, or is it going to be equal to 1, or is it going to be less than 1? What's the biggest current in the transistor? Emitter. So the big guy's on bottom, collector current is on top. So this guy is always going to be less than 1. Now it's going to be up in the 9s, right? You understand? 0.9. We know that collector current and emitter current are almost equal to each other. We can calculate, and the problem is we're going to use alpha, but they don't give it in the data sheets. And why don't they give it in the data sheet? So it's because it's so easy to calculate. So basically, this is the basic formula for alpha, DC alpha reference. It's beta over beta plus 1. Huh? It's going to be less than 1. Always less than 1. Why, Charles? Why? Because the emitter current's on the bottom. The emitter current is the biggest current in the transistor. So if it's the biggest current in the transistor, if the bottom number is bigger than the top number, you'll always get a fraction. If the top number is bigger than the bottom number, then you'll get a number that's greater than 1. So what we do is this will always be a number less than 1. We're going to run into alpha when we get into the common collector amplifier. The 2 amplifiers that we're going to spend most time with is we're going to spend common emitter. It's probably the most widely used amplifier, followed by the common collector. We'll see why when we get into them. But common collector, these are your current amplifiers. These guys right here will give you a ton of current gain. but they don't give the alpha in the data sheet. And why? Because it's just like they don't give us IZ max in the data sheet. Because they give you the wattage, they give you the maximum wattage, they give you the Zener voltage, and they understand that if you understand electronics, you know that I is equal to P over V, right? So we calculate the maximum current. Well, what they do here is they don't give us the alpha because it's so easy to calculate. And what is it? Now you can get, hopefully you can definitely see this is going to be less than 1. This is going to be less than 1. Because even though beta's on the top and the bottom of the equation, on the bottom one I add 1 to what the beta every time. So this is the way we can come up and get alpha. We're not going to use it that much, but it'll explain some of the things that we're going to have to talk about. Common base, we'll touch on the common base. Common bases are used in extremely high frequency applications, and we're not going to run into that much in this class. So the two types we're going to concentrate on is common emitter and common collector. And then we'll start hooking them up in what we call stages. Stages means you take one transistor or amplifier and you run it into another amplifier. And we'll figure out why we do that too. But usually power amps are made of multiple stages. So if you want 400 watts, you can't get 400 watts out of one transistor. So what you do is you'll go through one transistor amplifier to get so many watts, and you'll take that and feed it into another one and feed it into another one, and you keep getting more power until you get out to the final stages. Because your big power transistors require a lot of current. You know, if they've got a beta of 30 and you're trying to get 15 amps out of it, right? You understand? That means you still got to put a lot of current into them to get that, even though you still get a gain. Now this is not covered very well in the book, but we're going to have to do this is when we start talking about these different voltages. So what we're going to do, depending on where we're at, we're going to give these voltages different names. And all these are relative to common. So that means dB is going to be, I'm going to measure between what? Between the circuit common and the base lead. DC will be, we're going to measure between the circuit common and the collector lead. And then what's going to, VE, we're going to measure between circuit common and the emitter lead. Okay, so that's why we're going to designate these voltage measurements. And when we calculate them, we're going to learn how to calculate. Guess what laws we're going to use to calculate these bias voltages? Huh? Kirchhoff's law, Ohm's law, Watt's law. Watt's law when we get into power. So our two main formulas, we're just going to have to figure out how to apply them to transistors. Series circuits, series parallel circuits. And they're not hard series parallel circuits, guys. They're really easy. Real easy. Three elements or 2 elements in a series circuit. And then we calculate them separate from each other. So this is what we looked at. This would be a common emitter. Why is it a common emitter? Because here's my input. So this battery is common to, this is my signal battery. It's common to this. And then this is my output battery. It's common and the emitter is common. So this would be a common emitter arrangement. Now eventually we're going to have to learn how to bias this with one battery. We start off when we teach transistors, we use 2 batteries because it's easy to teach. All I would do for a PNP is just reverse the batteries. And they work exactly the same. My current calculations would be the same. My voltage calculations would be the same. It's just that my voltages now would be minus instead of being plus. So here's VB. So VB, what I would do is I would come up and I would take my voltmeter and I would put it right here, right? So that'd be VB. VC, we would measure it from the collector lead all the way down to the circuit common. And then VE, we would measure it here from here. Now, right now, VE is going to be equal to 0 because we don't have anything in the emitter. We don't have an emitter resistor. But later on, we're going to add a emitter resistor down there, and it's still going to be common emitter, and we'll talk about why. Okay? Okay so far. Okay, then we turn up with voltages that we measure between leads. And this is the common right here. So this is common. This is my meter common. So it's not circuit common, it's meter common. Y'all understand the difference now, right? So meter common is the black lead. And it's not circuit common because you can put that meter lead anywhere inside a circuit and it's not going to hurt anything as long as you don't touch them together. So what we would do, voltage collector to emitter, base to emitter, it means I would take my black lead and I would put it on the emitter. So this would be my black lead. And then I would take my red lead and put it on the base. And that's why we measure that. A collector to emitter is an extremely important measurement. So this is the one we're going to figure out all the time because this measurement determines what region the transistor is operating in. So if VB is less than a volt, so voltage collector to emitter, if it's less than a volt, then we're going to say it's saturated. If VCE is equal to my power voltage, my collector voltage, we'll talk about that later on. We call that VCC. We're going to say it's what? Cutoff. And if it's somewhere in between, if it's greater than 1 volt or less than VCC, we're going to say it's active. So this is a very, very important region for us to measure because this will tell us what region the transistor is operating. And now that we know this, so this is a lot of what we do to troubleshoot a transistor amplifier is we measure these bias voltages. And then a lot of times we can tell what's wrong with the amplifier just by the bias voltage. So this is a diagram showing you how we measure those. Are we okay? So this is how we're going to refer to that. Then we get to the power supplies themselves. So we double the letters indicating that is a power source. So VBB would be a DC source connected to the base. VCC is the power source if it's connected to the what? Collector. VEE, which they don't show here, but we're going to move to that sooner or later, it's going to be if the power source is connected to the emitter. And the emitter is not common, right? You understand that? So we assume these are all made relative to circuit common, except for these guys. But the common lead is on the right. So VCB would be you put your black lead on the base, you put your red lead on the collector. VCE, you'd put your black lead on the emitter, you put your red lead on the collector. VBE, you'd put your black lead on the emitter, you'd put your red lead on the base. Are we okay? VCC, you put your black lead on circuit common, and it would be the voltage connected toward the collector. Not necessarily on the collector. So right here, this is VCC. If I wanted to measure VCC, I would not measure it right there. I would measure it right here. I'd measure it across the actual voltage source itself. If I measured it right here, relative to common, then it's not VC. It's DC. Are we okay? Everybody okay? Because we're going to use these terms a lot. I'm listening. We okay? Power supply external voltages are designated with 2-letter subscripts depending on the transistor lead to which the power is connected. So if we connect it up toward the collector lead, it's going to be called what? VCC. If we connect it, the power is connected up to the base lead, we're going to call that VBB. If it's connected to the emitter, we're going to call that VEE. And you'll see this pop up in microprocessors. You'll see this pop up every once in a while for FETs. So we have VSS, VGG, and VDD in FETs. No, that's if we do it. Okay. You understand? So later on, we're going to move into a transistor amplifier that's going to look like this. I'm going to put a resistor right there. I'm going to put a resistor right there. I'm going to come over here and I'm going to put a resistor right there. I'm going to put a resistor right here. I'm going to put a common right there. I'm going to put a common right there. I'm going to put a resistor right here. And up here, I'm going to put a power supply. What's that power supply up there going to be called? It's going to be two letters. They're going to be the same. It's going to be VCC, it's going to be VBB, or it's going to be VEE. And we refer to this as VCC because this is the main power source for a collector. We call it VCC, and that's what we designate. And this can be anything. In digital TTL, we call it. In digital, it's a designated voltage, 5 volts plus or minus 5%. It's called VCC. So if you look at any digital logic gate, you're going to see a bunch of VCCs on there. We can look at the microprocessors and see a bunch of VCCs. In transistors, it could be any voltage. The voltage depends on the voltage, and we'll figure out how we can bias it. So normally, we're going to figure out how we can bias it with one battery, right? You understand? We don't want two completely different power sources to make the dang thing work. We can figure out how to use resistors to get voltages. So what can we get with resistors? We can cause voltage drops in resistors. So we'll figure out before long how we can bias all these things with one source. So when we're talking about voltage sources, and like here, it's not connected directly to the collector. Here it's connected to the collector through a resistor. Right? You understand that? So this is the battery. This is the DC source connected to the base. It's connected to the base, not to the base. It's controlling the voltage on the base. So we call this guy right here what? VBB. This guy right here is controlling the voltage that is applied to the collector. So we call this guy what? VCC. Now if I measure this voltage right here, we call that voltage collector to emitter. So here we're talking about the voltage across the leads, and we give you the letters, right? It's just that all you got to know is the one on the right is your common. This is where you measure it in relative to. And if I measure the voltage right here, what would we call that? We call that VBE. Where's your common going to be at? It's going to be on the emitter. This voltage right here, we would call this VCB. So this would tell you how you would measure those voltages. Of course, guess what? We can calculate all these. And once I've calculated them, then my measurements mean something. And this is what we're trying to do. And we get a feeling of what these things normally are, then we don't have to do the calculations anymore. And it all depends on how we operate the transistor. If we operate it in the active region, if we operate it in saturation, or we operate in cutoff. And we never operate it just in saturation. We never operate it just in cutoff. If we operate it like a switch, we're switching it between what? Saturation and cutoff. If I was going to always operate it in saturation, I'd use a straight piece of wire. If I was going to always operate it in cutoff, I just wouldn't put a wire there. Right? You understand? So if I'm going to operate it, so that's when we operate it like a switch, we switch it to saturation to cut things on, and we cut it off to turn them off. But we get that gain, right? You understand? So what's controlling it? So it allows me to just touch a little tiny switch over here on my wall and turn on light. So they like Kohler's got the sink. You can go over and just touch the sink, turn the thing off and on. Well, we got some type of solid state device that gives us a big current gain. It's picking me up, right? the voltage that's on me. We've always got a voltage on us, right? You understand that? So it's picking up that little voltage that's induced into my body and triggering a solid state device to open up a valve somewhere. So this is what's so neat, is these two things are totally separate from each other. So I've got my base that's looking at a diode, and it's controlling the current over here. And they're basically separated from each other. So what we'll find out is we're going to solve this like two different series circuits. So y'all could solve this right here right now. If I just tell you a couple of things. So this is a true amplifier. We're not going to look at the inputs and the outputs. We call this a voltage divider bias, and we're going to figure out later on. Now VBB is set by this resistor. VBE is set by that resistor right there. So could you calculate, if I gave you this voltage and I gave you the size of these two resistors, could you calculate the voltage drop across that resistor right there? If I call this R2 and I call this R1, could you calculate the voltage drop across R1? Yes or no? Using Ohm's law, right? I mean, it'd be very easy. Well, as soon as you calculate the voltage drop across R1, you've calculated VB. Now, does that tell me the voltage drop right there? Well, what this is going to be VB. So VE would be equal to VB minus 0.7. Now, if I know minus 0.7, so that means if I've got 3 volts right there, what would I have right here? Well, right here I'd have 2.3 volts. If I know the size of that resistor right there, what can I calculate? If I know the voltage drop across the resistor, and I know the size of the resistor, what can I calculate? We calculate current. So if I can calculate current, what does that mean? Well, that's going to give me emitter current, but for all practical purposes, we're going to assume that emitter current and collector current are equal to each other. So that means if I can calculate that current flow, then I can calculate my collector current. Because I'm going to use IE and IC, I'm going to use them as being equal even though they're not, right? You understand that? Okay, so if I can calculate that, if I know the size of that resistor, now I know the current flow through it, then I can calculate what? I can calculate the voltage drop across that resistor. Then I can use Kirchhoff's law. If I know the voltage drop across this resistor and the voltage drop across that resistor, then I can calculate voltage collector to emitter using Kirchhoff's law. I just subtract everything out, and that would give me the voltage drop across the there. And I've solved for this transistor circuit. Using what? The only thing I had to learn is that VE is going to be 7/10 of a volt less than what? VB. Guys, that's all there is to it. Of course, there's going to be a lot more. We have to have a method of calculating gain and understanding these resistors. But this right here, we're biasing this with a single power supply. But what we do is we treat this as one circuit, and we treat that as one circuit. So we solve for this, and then I use that 7/10 of a volt to move over to this other side and solve for that. We treat them like two different series circuits. And they're actually series parallel, but all we do is work on them like what? They're two series circuits. And now you got the math. Using what law? We usually use the voltage divider formula over here because we don't need to know the voltage across that guy. All we need to know is the voltage across R1. Calculate the voltage across R1, subtract 7/10 across it. That'll give you the voltage drop across V. That'll be voltage on VE. That would be answer. So circuits analysis. So this is a switch. We can do this all day long. So what would we do? First of all, what would I do? What would I need to know? Let's see. I'm going to calculate this circuit. What would I need to know? Tell me. Tell me things I need to know. I need to know the voltages. Okay, so we can make up something. So let's make this 5 volts, and let's make this 15 volts. Okay, so what else do I need to know now? I need to know the size of those resistors. Okay, so we'll see if it's saturated or not. So let's say right here I use a 1K. Okay, what else do I need to know now? I need to know RC, so we'll make up something. I know this is not going to work out. Okay, what else do I need to know? No, don't know enough. I could calculate this circuit over here, so I could say, okay, what would this resistor right here drop? What's VB going to drop? What's VB going to drop? Kirchhoff's law says the sums of the voltage drop in the series loop. Here's my series loop right there. Kirchhoff's law says the sums of the voltage drops in the series loop has to equal to the applied voltage. So how much will that resistor right there drop? I'm killing me. How much will that resistor right there drop? No, it's 5 volts. What? What's that? 4.3 volts. Why? 7/10 for the diode. Y'all keep throwing that thing out the window. We even have problems with that in power supply. So that's going to drop 4.3 volts. Okay. So what can I calculate now? What can I calculate? I know the voltage drop across the resistor. I know the size of the resistor. What can I calculate? Voltage drop size. I know two things. What can I calculate? Current. Good. So I'd come up here and I'd say IB. That's what we call the base current, right? So IB would be equal to 4.3 divided by 1K. So it's going to be equal to what? 4.3 milliamps. Okay, what do I need to know now? Before I go on, what do I need to know now? No, 7/10 of a volt, we don't have anything to work with over here because we don't have an emitter resistor. That's a good point, but I don't have an emitter resistor. All I know is this right here is going to be 0.7. This is going to be 0. So that's not telling me anything. A while ago we had a resistor in the emitter, so we could subtract that 7/10. Here we don't have anything to work with. Good point though. What else do we need to know about the transistor? What else do we need to know? What do we need to know about the transistor? What do we need to know about the transistor? We need to know the beta of the transistor. Where am I going to get that information at? Data sheet. So I go to data sheets and I look what the beta was. So let's say I had a beta just for practical purposes, so I think it's going to saturate. Okay, so where's my cotton? Let's see, we got a, what do we got over there? We got a 10K. We got 15 volts. So let's say it has a beta just for the heck of it. Let's say it has a beta of 3. That's a very low beta. But so what would I do now? So over here I know I got 4.3 milliamps. So what would I do now? 10K is not going to work. We're going to saturate this thing, but that's okay. Y'all get a feel of this. 4.3 milliamps. What am I going to do now? I know the beta of the transistor. So beta is equal to IC over IB. Well, I know IB. I know the beta. So what can I do? I know the beta. I know this. I know IC. I know this guy. So what can I do? Huh? Well, I can put this in a little thing right here. I can say beta. It's actually beta. I can say is equal to, and put it in this little thing we learned about in in DC, right? Put in this little equation real. So beta is equal to IC over IB. I know beta, I know IB. So how would I solve for IC? Right, so we take the beta, which I said was 3, we'd multiply that times the 4.3 milliamps, and then that would give me IC. What's IC? This is not going to work, guys. 12.9 milliamps. So we're saturated. Because why? So I say RC would drop, so VRC would be equal to IC, which would be 12.9 milliamps times 10K. What does that come up and give me? I knew this wasn't going to work. So what does that give me? $120 volts. What's the problem? Yeah, we can't drop more than the power supply. But you get an idea of what we can do, right? You understand? Of course, I chose values off the right. Yeah, this guy right here, so we're saturated. We could do this, but the problem is, as soon as this guy right here dropped 15 volts, then there's nothing left over. And you'd be surprised how many people write down that they're going to drop. They would write down it's going to drop 120 volts, and there's only the volts. Where does the voltage come from? The voltage don't come from the transistor. Where does the voltage come from? From that power supply. So we can't drop 120 volts in a circuit and only have 15 volts applied. In DC, guys do that all the time. They do their math. They have a 20 volt power supply and they say, oh, resistor drops 200 volts. And they'll just write everything down. They keep on going and not realizing what? That's impossible. You can't drop. So this transistor, as soon as this guy right here dropped 15 volts and everything, I could put 100 amps of base current and burn up my transistor, but it wouldn't work. But see, once we know this, once we know the beta of the transistor, once we know this, and then we can do a lot of basic math. It's just multiplication. It's not really heavy math, right? Okay. That's what I gave. You'd be dead in the water. That would be like saying I work 15 hours, how much do I get paid? And you don't know what your base salary is. So you got 15, so you multiply something by 15, you still don't know what you're supposed to make because you didn't know what you was getting paid per hour. So we don't know the game, but the problem is that information is available. Now it's not really good information because beta moves around. But for math purposes, it gives us a really good indication of what beta is. So what we'll do when we get into amplifier circuits is we'll set the beta of the circuit. And all it's got to do, so what we'll look at it, when we look at the data sheets, we'll see beta, it's got a minimum beta and it's got a maximum beta. All we know is the beta is going to be where? Somewhere between the what? The minimum and the maximum. So when we start getting into transistor amplifiers, you'll see that the engineer can design the beta into a circuit. It's just going to have to be somewhere between the transistor's what? Minimum and maximum. As long as he or she designs it in that, you're okay. But if we just turn that sucker loose, all we know is that it's going to be somewhere between the what? The minimum and the maximum. So when we saturate a switch, we're going to choose, what would you think we would use when we saturate the switch? Will we use minimum beta or will we use maximum beta? What would you think? Which one's guaranteed? Minimum, yeah, minimum. So I can always depend on minimum beta. I can't depend on maximum beta. I can always depend on minimum beta. So when we design a saturated switch, we'll just look at the data sheets and we'll use minimum beta. And then we'll design it around minimum beta. The beta's, once the transistor's saturated, it's what? It's saturated, right? You understand that? So if the transistor has a beta bigger than minimum, it's not going to hurt anything. I mean, it'll still saturate. It's just that what we're trying to do is make sure it saturates in every situation you could be in, whether it's running in Alabama in the summertime or it's running up in Adak, Alaska, right? Why not mention Adak, Alaska? Because I had the opportunity to go up there when I was in the Navy. And I was in the Navy too. I'm going to tell you what we used to say about Adak, Alaska. Now go ahead and take a break. We'll start looking at saturated switches. So let's see if this will work out. Go ahead and do the math.